This is OwlUp, where learning happens in minutes, not hours. For a deeper journey, explore all our courses at owlup.co. Now, let's dive in. Chapter 4 of How AI Thinks, Understanding Large Language Models, Training Giants, the Data and Models Behind LLMs. In this chapter, you'll learn: explain the data requirements for LLM training. Let's dive in. Some of the world's most powerful AIs were trained on text you wrote years ago and forgot about. A late-night blog rant, a code snippet on GitHub, a review on a shopping site, quietly scooped up, cleaned, or not, and turned into the thoughts of a giant language model. Billions of parameters and clever architecture aren't enough to make an LLM useful. What really shapes its personality is which pieces of the internet it digests, how often they appear, and how carefully they're filtered or amplified. A sarcastic subreddit that shows up a billion times can tug a model's tone as strongly as a whole library of textbooks. On the flip side, a relatively tiny set of high-quality sources, well-edited books, solid documentation, carefully labeled examples, can disproportionately improve reasoning and factual accuracy. Behind every headline model is an invisible set of choices: which languages get priority, how much code versus dialogue, which domains are overrepresented, which are missing entirely. Those choices don't just affect benchmarks, they determine whose voices the model echoes, which edge cases it handles gracefully, and where it breaks in surprising, sometimes uncomfortable ways. That hidden pipeline from messy internet to polished model is mostly invisible, even to many people working in tech. In practice, teams stitch together huge datasets from web crawls, code repositories, academic papers, subtitles, forums, and licensed archives, then run waves of filters, heuristics, and learned classifiers over them. Some runs aggressively strip profanity or hate speech, others focus on removing near duplicates, spam, or content farms. Every pass trades something off: safety versus coverage, diversity versus consistency, scale versus trustworthiness. Those trade-offs quietly shape what the model seems to know. There's a second, equally important half to training giants: the models themselves and the hardware that can actually move all this data through them. Start with size. You've already heard numbers like 70 billion or 175 billion parameters. What matters here is how those parameters interact with the data budget. DeepMind's chinchilla work flipped the old intuition of just build a bigger model. For a given amount of compute, it's more efficient to balance model size and training tokens than to max out either dimension. That's why current frontier systems quietly chase an internal ratio, on the order of tens of training tokens per parameter, rather than a single brag-worthy number. Architecture choices layer on top. Palm 2, for instance, mixes dense layers with sparse mixture of experts (MOE) blocks. Only a subset of experts activate for each input, so you can carry far more total parameters without paying the full compute cost every step. It's a way of having many specialized subbrains while keeping the electric bill barely manageable. All of this runs on specialized clusters, racks of GPUs or TPUs stitched together with high-bandwidth interconnects. Training a modern 70 billion parameter model on trillions of tokens means orchestrating thousands of chips across weeks, slicing the model across devices, model parallelism, and slicing the data across others, data parallelism, while constantly shuffling gradients around the network. Failures aren't rare. Resilience and clever scheduling become part of training science. And then there's the stage after raw training. Techniques like reinforcement learning from human feedback reshape how a model responds without re-ingesting the entire web. Retrieval augmented generation bolts on external search or databases, so the system consults fresh knowledge instead of memorizing everything. Data-centric approaches iterate on which examples are most informative, rather than simply adding more. Put together, the frontier isn't just bigger models on more text. It's a three-way negotiation between smarter data selection, more nuanced architectures, and infrastructure that can barely keep up. Think about what better data actually looks like in practice. When teams refine a dataset, they don't just delete bad pages, they rebalance what the model sees. For a coding assistant, that might mean deliberately upweighting tests, documentation, and bug reports so the model picks up debugging patterns instead of only polished library code. For a medical QA model, it might mean emphasizing guidelines, clinical trial summaries, and carefully de-identified case notes, then downweighting speculative blog posts that sound confident but aren't peer-reviewed. Companies also create tiny surgical datasets, thousands, not billions, of examples focused on tricky behaviors, following multi-step instructions, refusing unsafe requests, handling mixed languages. Those examples become the pressure points for RLHF or other fine-tuning, nudging an otherwise generic model into something that behaves like a specialized assistant without retraining everything from scratch. Your challenge this week: pick one AI tool you use and try to reverse engineer its training priorities. For each of 3 tasks you give it, say, a coding question, a legal-sounding question, and a pop culture question, write down what kinds of sources it probably leans on: docs, forums, news, social chatter. Where it seems cautious versus overconfident. Which domains it handles with nuance, and which feel shallow or oddly biased. By the end of the week, compare notes. You'll start to see patterns, places where careful curation likely happened, and places where you're bumping into the rough edges of the underlying data. Regulation, economics, and engineering are quietly rewiring how these systems grow up. As rules emerge about provenance and consent, models may need receipts for what they've seen, much like audit trails in finance. Energy costs will push teams toward leaner, more focused training, favoring models that excel in narrow domains over general chatterboxes. And as synthetic data loops in, we'll face a new puzzle: how to keep models from overlearning their own reflections. In the next few years, training may look less like a one-off boot camp and more like continuous education. Models refreshed on live streams of law, science, and culture, with every update logged like edits in a shared document. As we pick what goes in, we're quietly drafting a curriculum for how machines, and maybe societies, learn. Here's your challenge this week: design and run a mini pre-training plus fine-tuning pipeline on a tiny domain you care about, for example, cooking recipes, Python snippets, or company FAQs, using an open-source model like Llama or Mistral. By tonight, assemble a pre-training corpus of at least 200 raw text examples and a separate instruction set of 30 to 50 prompt response pairs. Then actually fine-tune or LoRa-tune the model on both stages, first raw text, then instructions. Before and after training, ask the model the same 5 domain-specific questions and paste the responses side by side to compare how pre-training versus fine-tuning changed its behavior. This was OwlUp, your daily step forward. This series continues with more chapters on OwlUp.co. Visit OwlUp.co to access the complete course and continue your learning journey. See you there!